Hi everyone, Greg here. So today I'm going to talk about hashing. Now, hashing is a very important topic for programmers, and I do expect this is going to be a very important video in the history of my channel. This is probably a video that I'm going to be referring to a lot in the future. So I've shown this diagram before. It's a very important diagram, so I'm showing it here now again. So the beginner programmer believes that programming is just about writing code. The competent programmer understands that programming is fundamentally about problem solving. The competent programmer will have a large number of tools in his toolbox. Hashing is one of those, and the competent programmers always make sure that he understands the fundamentals of how his tools actually work. So understanding what hashing is exactly, how it works, and most importantly, why it is actually useful, that is what we're going to look at today. So hashing. What it is, fundamentally, it is an algorithm. Every algorithm can be thought of as a system. A system has this structure. It has an input, some processing, and output. Sometimes a system also has storage. In our case, we're not concerned about that. The input of a hashing function is any data, any binary data of arbitrary length. It could be a text, it could be an image, video, MP3, music, whatever. The output is fixed length. If we take, for example, the SHA-256, that's an example of a hashing algorithm, which stands for Secure Hashing Algorithm 256. We're going to discuss in a minute what that secure is supposed to mean there. But 256 simply refers to the length of the output, 256 bits. 256 bits is, of course, 32 bytes. So the output for this particular hashing algorithm is always 32 bytes. So 32 bytes, which traditionally are displayed as a hexadecimal number. So the exact details of how the hashing does occur, for the purpose of this video, we're going to treat this as a black box. We're not really going to concern ourselves with exactly how this is done. SHA-256 is an algorithm in the public domain. You can look it up if you care to know how it is. Suffice to say that hashing algorithms typically are a combination of shifts and exclusive ORs, which are being performed iteratively. That is to say, it's been done over and over again. So basically, the important thing to realize is that the hashing algorithm is a function which will scramble up your data in some way and produce a fixed length output. That number doesn't really mean anything. It's not an average. It's not some kind of symbolic representation or anything like that. It's just a number. The exact process by which this is done is not random, however. There are certain conditions that the hashing algorithm must comply with for it to be a proper hash. One of those is determinism. So that means that exactly the same input does always lead to exactly the same output. Another one is the irreversibility, right? So if you have the output, if you know what the output is, you can look at the hash. There is no way you can tell what the original input was. Even when the hashing algorithm itself is in the public domain, you can look at it, you have the algorithm, you have the output, there is no way you can infer from that what the input was. This might sound a little strange to some. It's like, could you not just take the output, perform the algorithm in reverse, and then figure out what the input was? Well, no, the algorithm is specifically designed in such a way that this is not going to work. So if we take a very simplistic example, if we consider the addition, right, let's say that the input is just two numbers and that the output is one number. If we do the addition and you find out that the number is 7, what was the input? Was it 5 and 2? Was it 3 and 4? Was it 10 and -3? Well, you don't know and you have no way of knowing, right? And the hashing algorithm is a much more complex algorithm than a simple addition, and basically reversing it is simply impossible. The only way that you can kind of do that is through brute force. So if you can come up with a guess as to what the input could have been and you pass it through the same algorithm, then you can compare that output with the hash that you're actually trying to crack. This might be a way of doing it. Obviously, when you have absolutely no idea what the input was, this is not a practical method. Then the third property, which is really more like a consequence of the second property, is that a very minute change in the input will lead to a very big change in the output. So imagine the following situation. Imagine that you have a particular hash and you're trying to figure out what the input was. Well, you could start with a random input. You could put it through that same hashing function and look at the output. Then you could make a change to the input and then look how that changes the output and see if that gets you closer or further away from the hash that you're trying to crack. And based on that, you keep tweaking the input to just get closer and closer to the hash that you're trying to crack, right? So that third property is really something which ensures that this approach is not going to work, and therefore ensures that the hashing algorithm is in effect truly not reversible. Okay, so that's basically what a hashing algorithm is. What is also important to note here is the idea of collisions, right? So if you have any input of arbitrary length, that is to say, you have infinite possibilities for the input, but you only have finite fixed length output, that means that collisions are going to be inevitable. And what collisions means is simply two different inputs which lead to the same output. Those collisions are okay. In fact, they are, again, inevitable. They are okay as long as they are very difficult to find. So again, let's say that you have a particular hash and you're trying to crack it. It is very difficult to find any input that will lead to that exact hash, right? So you wouldn't necessarily have to find the original input. If just finding any other input in some cases might be good enough, but because collisions are far and few between, even that is very difficult to do. What secure means is that it is, if not impossible, then at the very least very unlikely and very expensive in terms of resources, in terms of computing power, to find those collisions. Basically, the notion that you would be able to reverse a hash, or that you would find a different input leading to the same hash, you can treat it as basically impossible, because it would take so much effort and time and resources in order to achieve that. So that's basically what secure means here, is that the idea is that finding such a collision, finding a different input that will lead to that output, is basically so difficult that you can basically not concern yourself with it and decide that it's just not going to happen. Okay, so that's what a hash fundamentally is. Now you might ask yourself, why? Why would you care about a hashing function? There are in fact quite a few situations where hashing functions turn out to be very useful. Okay, so a first use that I'm going to touch on just very briefly is Bitcoin and various other cryptocurrencies. They rely very heavily on hashing. I'm not going to explain here how that works. I did write a book about that a couple of years ago. It is available for free from my website. So you can go to bitcoin.greging.com and you can download this ebook there for free. And it will explain exactly how hashing is involved in creating something like a cryptocurrency. It's going to explain exactly what a blockchain is. It's going to explain exactly what mining is. So if you want to know more about that, you can read all about it in that free ebook. I am not going to go into all this here. So the next thing I want to discuss is how to store a password. This is probably the first thing that is really going to be of interest to many. How do you actually properly store passwords? So let's first discuss the naive way, the really bad way. The way you do that is you just have a plain text password in your database. When the user types in their password, you just check it with the password that you have in the database. You see if there is a match, and if there is, you log the person in. So why is that a really bad idea? Well, obviously, if the hacker succeeds in breaking into your database, the hacker can simply read all the passwords. On top of that, the staff that's working at that company, they might have access to the database, and they might be able to read all the passwords. So what is a much better way of doing it? Well, if you have a company like Google, a company like that does definitely not store passwords in plain text. In fact, Google does not know your password. That might sound like a strange statement, but it's true. Google does not know what your password is. If you have a Gmail account or a YouTube account or something like that, Google does not know your password. And you can tell that they don't know your password because if you forget your password, you click on that link, forgot your password, they are not sending you your password. They are just going to give you an opportunity to reset your password. Okay, so if they don't know your password, how can you possibly log in? Well, a slightly better way than the naive way, but it's not yet good, is you're going to store hashed passwords. So basically what you're going to do, you're going to take the password when the user originally creates the account. And they're telling you, this is the password I want to use. You take that password and you create a hash. And then you put that hash into the database. The plaintext version of that password, once you've created your hash, you just throw it away. You don't remember it. You don't know what it is. The next time that the user wants to log in, they give you their password. You take a hash of the password that they've just given you, and you see if the hash that you have matches the hash that you have in the database. Again, remember it's deterministic. So every time someone gives you the same password, the hash is going to be the same. So you just check if the hashes do match. If so, then you log the person in. Okay, this is slightly better because now if hackers break into your database, they cannot actually read the passwords directly. They're hash passwords. Now, why am I saying that this is still not a very good way? Well, hackers could hash an entire dictionary, and they could look for matches between some of the accounts and the words in the dictionary. And most people use really bad passwords. They use ordinary dictionary words, so there's likely to be a lot of matches there. So what is the proper way? The proper way to do it is to do it with a salted hash. So what is a salted hash? Basically, you take the password, the plain text password, you add salt. So salt is basically a string that you concatenate to the password. And then you take the hash of that. And it's actually better if you use a different salt for every single account. So the salt could be a combination of their username and maybe the date and time that they first created their account. Something that's unique to that user. So with a salted hash, now it is very, very difficult to figure out what the password was. You would have to know not just the password, but also the salt. And it is not as important that the salt is secret, especially when you have a different salt for every user, because even when you know the salt, you basically still have to brute force your way through this and try every single word in the dictionary to see if there's going to be a match after you perform a hash of every single word in the dictionary with that particular salt. So while that would work, this is going to still be very resource intensive and very time consuming, and it's not very practical. So also do remember that with a secure hash, collisions are far and few between. So the likelihood that you're going to find two dictionary words that are going to hash to the same value is very, very small. Also do remember that if you have just a slight change in the input, you have a very different output. So even if two users use very similar words, let's say one uses the word as a singular and the other uses the word as a plural, they're going to give very different hashes. And especially if you have unique salt that you add to that, the hashes are going to be very different, even if there's just an extra letter S in there somewhere at the end of the password. Okay, so that was a salted hash, and that is basically the proper way of storing passwords. Okay, so the next concept I would like to talk about is the idea of a checksum. So let's say that you download a piece of open source free software. You download it, let's say, from a mirror, and you want to make sure that you download the legitimate thing and not something that is laced with malware. You could look at the checksum that will be provided by the official company or organization which publishes the software. So the checksum is basically just a hash of the software. You could download the software from that mirror, take a hash of the software you've just downloaded, and compare it with the official checksum that is published on the website and see if they match. If they do match, then you will know that number one, no corruption happened during download, and number two, you will know that there was no malware included. Now, back in the olden days, there was something called MD5. MD5 is a hashing algorithm. It is something that was designed when hardware was a lot less powerful than today. And MD5 was back in the day used a lot for checksums. Now, what a hacker would be able to do today is take a legit piece of software, add malware, and then add a piece of junk. Then take a hash of this with MD5 and see if the hash produced is the same as the official checksum. If it's not, and obviously it wouldn't be, well, then what you do is you tweak the junk and you take a hash again and see if this time you have a match. And you just keep doing that zillions of times until you do have a match. So this is a brute force attack. Considering how old MD5 is, and considering how powerful hardware is today, this is actually feasible. And what I'm describing now is not just purely theoretical. This has actually been successfully pulled off by hackers in real life. So for this reason, nowadays MD5 is considered unsafe and should never be used ever again in a context where security is an issue. So the checksum is basically a hash to check the legitimacy of a piece of software. You can also imagine a situation where you need to download a file from a trusted source, and all you really want to know is, has the file been updated? And if it has, then you want to download it again. But you only want to download it if it has been updated. You don't want to download it every time if there is no need for it. So you take a hash of the current version of the file that you have, you compare it with the hash of the file on the server, and if those two match, then you know the two are almost certainly identical and you don't need to download again. So there is this YouTuber programmer, Casey Muratori, and he developed the Meow hash. The Meow hash is a hash which is designed to be fast, and it is intended for exactly that kind of purpose. Okay, so the next thing I would like to talk about is encryption. Believe it or not, there actually does exist a perfect encryption algorithm. It is perfect with two caveats, and I'll mention them in a second. The one-time pad is based on the exclusive OR. I'm assuming that you know what logic gates are and that you are familiar with the exclusive OR. If you're not, I've already made a video about what happens inside a computer. There will be a link in the description and I suggest you check it out. So here is a truth table about the exclusive OR. Again, I'm assuming this makes perfect sense to you. So traditionally in encryption, we consider Alice and Bob, and Alice is trying to send a message to Bob. So how is she going to do that? She's going to take her message one byte at a time, and she's going to perform the exclusive OR with a list of random numbers. Then she's going to send that cipher, that encrypted message. Bob on the other side will do the same operation in reverse. He will take the cipher, he will perform the exclusive OR with those random numbers, and he's going to retrieve the original message. So if Eve is eavesdropping, Eve cannot read the message because with genuinely random numbers, there's no actual pattern to the message. So the two caveats here is, number one, you must use genuinely random numbers. You cannot use pseudo-random numbers, and you cannot reuse the random numbers you've already used. So you must generate fresh random numbers every time. If you reuse that series of random numbers, then there is a pattern, and then that could potentially be figured out. So that's the first caveat, genuinely random numbers. The second one is that you must figure out a way to securely communicate that list of random numbers to Bob. So you can imagine that Alice and Bob meet in person. They know they will need to communicate at some point in the future remotely. They agree on a list of random numbers. Okay, so the next thing I'm going to share with you is my own encryption algorithm. This is an algorithm that I actually use for my own data. It is a variation on the one-time pad. So the way it works is you take a password, you concatenate the number 1 at the end of it, and then you take a hash of that. I use the SHA-256 hash. Then you get 32 bytes, and those 32 bytes substitute the random numbers that you would normally use in the one-time pad algorithm. What if your message is longer than 32 bytes? Well, then you take the password again, you concatenate the number 2, you take the hash again, and then you have an extra 32 bytes, and you continue to do that for the entire length of your message. Also remember, a property of the hash function is that a slight change in the input will lead to completely different output. So as you keep concatenating different numbers and you perform those different hashes, those hashes will all look very differently from one another. So this algorithm is a variation on the one-time pad, and that algorithm is not perfect. However, it is still very, very strong. And I'm going to show you this in code in a second, and as always, the links will be in the description for the GitLab. Okay, so now I'm going to show you the actual code. So what do I have in this directory here? I have number 1, a message. Okay, this is what I'm going to encrypt. So I'm reading the book June at the moment, and there's the movie coming out later this year, and I'm really enjoying the book so far. I'm about 70% in, and so I just have a quote here from Dune. So this is the message that I'm going to encrypt. What else do I have? I have the encryption algorithm. I did not write that myself. I just got it off the internet, and I am going to go ahead and I'm going to compile this. There you are. Now I have this .o file, and then here I have main. So the way that this is meant to be used is there will be an executable encrypt. I'm going to type in message.txt, and then I'm going to type in cipher.txt, and the message will go into this file. So from this file into that file, and in that you will have the encrypted text. Right, I'm going to demonstrate that in a second. But for now, let's actually look at the main.c. Main.c, so we have here this function, tech encrypt. So my personal library is called technical, so all of the functions that I take from my personal library, they will have this tech prefix. And here is basically the pre and post conditions of this function. So basically this function takes 3 variables: the message you want to encrypt, the length of the message, and then the password. Once you want to decrypt, you take the cipher, you replace message with the cipher. Again, the length will be the same, and then the same password again. So that's what it says here. The same function is to be used to decrypt. Don't use predictable passwords. If you lose the password, there is no way of recovering your data. You know what they say about great power comes great responsibility. This is a big toy for big boys. So if you lose your password, you lose your data. There is no backdoor, there's no loophole. This is strong encryption, and you just have to manage your passwords properly. You just have to make sure that you responsibly manage your data. If you lose the password, your data is encrypted. You're not getting it back. Okay, so just be aware of that this is really serious encryption. Okay, so here it talks about the potential pitfall. So basically, you'll have the message, the length, the password, and then it will return the cipher. That cipher is not a null terminated string. This will contain gibberish, and somewhere in there could be null characters, and those null characters are not the end of the string, which is part of the reason, well, it is the reason why you have to give the length here, because then when you want to decrypt, you take whatever was returned, that becomes the message here, and so this function is not looking at a null character anywhere in the message, so you have to give it the length. The password is just an ordinary null terminated string. Okay, so that's the pitfall. Right. So then we have a couple of string manipulation functions which are actually used by the encryption algorithm, and we have a couple of functions to manipulate the files, and you're going to see in a second why I'm using this. So here, this is the actual function. Okay, so these are a couple of checks on the input. And then here you see the SHA-256 hash is actually being computed. What else can I show you? So basically you have this character string to hash. You copy the password into this string. Here we have an integer step, which is set to 1. So step gets converted to a string. So num will contain the string. And then you concatenate to hash, which already has the password. You concatenate the number. So then you concatenate to hash, which already has the password. Now also gets the number added to it. You'd add one to step in case we have to do this again later. Then this to hash, which is the password and the number, you actually take the hash of this. The hash will be stored in this character array hash, and it's always 32 bytes in length. And then you do an exclusive OR between hash and your message, right? And you do that for the entire length of the message. And then when you run out of your 32 bytes, then you just end this loop. You go back here to see if you're done with the message, and if not, you just get the next to hash, step being 2 this time, and you just go through the loop in this way, and then it returns cipher. Okay, so that's not really complicated, and that's basically what I explained earlier. So now let's look at the main function. So I think this is pretty much self-explanatory. So basically you check whether you have 3 arguments. So the first argument will be the name of the program itself. So you need an extra 2, which is going to be the message, like one file containing the message and then the file containing the output. I just create this character pointer file input because that's just more convenient than using the second argument. So they're obviously numbered from 0, the second argument. Checking if the file does exist in the first place. Then getting the size of the file, getting the contents. This will return a buffer. In fact, what we could do here, we could do this. We don't really need to because we're really using, yeah, there's no real point in doing it because as soon as the program ends, this will be freed anyway, so it's not really necessary. But anyway, we're getting the contents of the file. We're calling this function TechEncrypt, where the magic happens. Pass on that buffer, the size of the buffer. So this the size of the file, right? And then the password. Now the password, you would not normally put your password like this in the code, right? Usually the password is coming from some user input. This is just a simple demonstration program. You're not supposed to use it as is. You're just supposed to use this as a starting point to create whatever application you want and to encrypt whatever data you need to encrypt. So it's all programmers watching this channel, so you're all able to take this function and then use it in a way that makes sense. So if you need to create a function that will basically request a password from the user, I'm assuming that you're all able to do this and you know how to deal with passwords properly. So this is just, I would normally not have the password like this, but this is just for the sake of a demonstration program, so that's fair enough. And then you just write the cipher to the file, which is the second argument. And that's basically it. That is basically it. So shall we look at it actually running? So hold on, what am I doing here? So now I have this file cipher.txt. If I try to look at the contents, then it is warning me that this is a binary file, and if I look at it, then you see that it's all gibberish. So this is actually the encrypted data. And now what if I want to decrypt? Well, I take the file which has the cipher in it and I output it to a new file. There we are. And now we see that this new file is here. And if I look at it, then I'm seeing that this is indeed the original data that I had. Okay, so that's basically how my encryption algorithm does work. And you can tell that it's actually very straightforward to use, right? Once all of the code is written and all the hard work has been done, all you really need to do is just call this function and pass on what you want to encrypt and the password. I mean, you can't make it simpler than that. Again, use it responsibly. This is basically all I wanted to tell you. So I hope you learned something. I hope you enjoyed. If you did, please consider giving me a like. Please give me a subscribe. And you should see on the screen other videos that I have made. And now you can even buy me a coffee if you want to. There is a coffee page there on the screen. So if you think this was very useful, if you think I deserved a free cup of coffee, then there is the link on the screen right now. So thanks again to everyone. Thanks to everybody who already did subscribe. And we're still climbing. We're still climbing in subscribers. It's not been that long since I did the special 256 subscriber special where I created the Dux programming language, and I said I would improve it if I ever make it to 512. So as I speak, we are at 429. So less than 100 to go before I have to make an improved version of Dux. So that's gonna be fun. So thanks again, and I see you in the next one.